Okay, good morning everyone, and thank you for your presence. So in the next, I don't know, maybe 40 minutes or so, I will give you a rapid introduction to some of the work that we are doing at Singapore University of Technology and Design in the area of secure design of cyber-physical systems. So I'll go through a quick introduction of what cyber-physical systems are and what are the issues that are being faced by many countries and by many organizations. And then I'll, toward the end, I will talk about a little bit about a new process that we are developing to test out these cyber-physical systems to find out how secure they are and how safe they are. So, first of all, what is a cyber-physical system? Of course, there are several definitions. I won't attempt a definition, but I'll just give you some examples. And so, first of all, an overall structure of a cyber-physical system. So, consider a plant. It could be a power generation plant, a water treatment plant, an oil and natural gas plant. So, that's a plant. So, most of the modern plants have a monitoring and control system. These monitoring and control systems are computers essentially, which are also known as SCADA, so supervisory control and data acquisition systems, PLCs, programmable logic controller, HMIs, etc. These are essentially standalone embedded computers that are continuously monitoring these plants and controlling them. Now, between the plant and the control system, the data and control flow, and there is a network that is responsible for this control flow. Some examples, of course, are water treatment and distribution systems, healthcare, pacemaker, defibrillator, the insulin pump, etc., energy, power generation, distribution, and smart metering, and of course, transportation, driverless cars, network systems, and so on. We at SCTD are focusing on water treatment and power generation, by which I mean we actually are developing realistic test beds to conduct experiments based on our techniques and the theories that we develop. So there are two key questions of interest to us. One is, how does one defend a cyber-physical system against cyber attacks? Okay? And the other is, how does one quantitatively assess the security level of a cyber-physical system, that is of its defense, that is prevention and detection of attacks, and response mechanisms. We all know that this, almost regardless of the defense mechanisms that are introduced into these systems, attackers are successful. If they spend a lot of time and money, they are eventually successful. So the question arises, once an attacker is successful, what does one do in order to defend the system so that it does not go into an unsafe state? So with that background, let me give you a brief, some data on what is the nature and magnitude of the cyber threats to these cyber-physical systems. So in the past few years, or in fact since 2001, there have been several attacks on cyber-physical systems, successful attacks. There have been many unsuccessful attacks, but there have been quite a few successful attacks also. So in 2001 in Queensland, Australia, 264,000 gallons of sewage were released in rivers and parks by means of an attack that a disgruntled employee launched. In 2006, in the United States, in the Harrisburg water filtering plant, again, there was a malware that was planted. In 2007, in the Tacoma Canal in Williams, California, a damaged computer was used to divert water. In 2008, of course, we all know the Stuxnet that was launched to destroy the Iranian uranium enrichment plant. It was successful to some extent. In 2012, more recently, the North Pole Toys, it's a toy company in Florida, that was attacked successfully. The result was that people who had ordered toys, they were getting the toys that they did not order, or they were not getting toys at all. They were getting empty boxes. So there are different types of attacks that have happened so far. These are, of course, in 2012. There is an organization called ICTer, Industrial Control Systems, Cyber Emergency Response Team in the United States, that tracks attacks and vulnerabilities in various systems. So the most recent, one of the most recent reports in 2013 indicated that they responded to 256 incidents, up from 197 in 2012. So this is increasing, of course. 151 of these incidents were in the energy sector, 50 incidents in critical manufacturing, And of course, there's a website that if you want, you can look at that, or the details of these attacks. Some of the sample attacks there was a Night Dragon attack in February 2010 that targeted global oil and petrochemical companies. And then in February 2010 again, there was a Nitro attack which targeted chemical compounds. And there was a pump shutdown in 2011 at a water utility in Illinois. Nothing very significant, but you can see that attempts are being made and they are successful. So energy sector, of course, as the network once said, America's water energy utilities face constant cyber espionage and denial of service attacks against industrial control systems, according to this team of specialists from the US Department of Homeland Security. Of course, this is America, but you never know when any country's infrastructure is attacked by the attackers. There have been lots of vulnerabilities that have been found and are being continuously found by ICTer analysts. For example, this is at Rockwell. Independent researcher Mathur of CyberTI has identified a fault generation vulnerability that can cause a denial of service in the Rockwell Automation Allen Bradley Micrologics PLC controller. Another in Siemens and Rockwell are two of the most commonly used programmable logic controllers, PLCs, in the world. And there, lots of vulnerabilities are being found in them. Every time they release a new version, some vulnerability is found. I won't go into the details of this. So, with that background, I hope I am able to let you at least think that this is an important problem, and researchers in the universities must get together with engineers and companies. And of course, I fully agree with our speaker that there's a need for technology transfer, not just sitting in our comfort zone and writing papers. And that's what we are trying to do at Singapore University of Technology and Design, in collaboration with Public Utility Board there and Sing Power. So let me now look at the points of attack in a cyber physical system. So this is a systems view, very, very high level systems view of a cyber physical system. So let's say this is my physical system that at any point in time has a state. And by state I mean the value of all the interesting variables, such as, for example, whether a generator is on or not, how much current is flowing on a certain bus, or what is the level of what is the pH level of water that is going out into the reservoir, and so on. So that's the state of the system at any point in time. The state of the system, the actual state of the system, is measured by a large, usually a very large, thousands of sensors that are sensing these individual state elements across the entire cyber physical system. And these state values are being sent to the control system. The purpose of the control system is to get this data from the sensors, make an estimate of the actual state of the system, because after all it is only getting an estimate of the state. So it makes an appropriate estimate of the state of the system, and then decides what control signals to send to the physical system. And it does so through actuators. So for example, it might turn a pump on, it might turn an additional generator on, or it might close a switch, and so on. So that's the overall structure, systems view of the cyber physical system. So X is this is the system state. What you get is Y, and what you estimate here is used to control the actuators. Now, of course, this link and this link between the sensor and the control system with the actuator are either wired. In most of the systems today, they are wired. I think there's a fire here. I think there's a fire here. You have to be careful. This is also not a cyber physical system. So you have to be careful. There is something burning here. You don't want this to just. So where was I? Okay. So this So these two links. Today, in most of the system, these are wired links, and they're more difficult to attack than wireless links. But many infrastructure companies, water, power, and so on, are now moving towards wireless. A lot of old people like me say, no, don't use wireless, but the youngsters want to use wireless for good reasons. Both of them have good reasons. But the fact is that wireless connectivity is now on the rise. And therefore, the attackers have a better chance of getting into the system. Now, what are the attack points in such systems? So, as I said, these two are the links, sensor to controller and controller to the actuator. And therefore, if a sensor, if this link is compromised, then the control system, instead of getting the data that the sensor is actually finding out, sensor actually, or the control system receives wrong data. So for example, the level of a water tank actually is, let's say, 4 feet, the controller gets 3 feet or 2 feet or whatever. If the speed of a cylinder in which uranium is being purified is, let's say, 100 rounds per minute, the speed that is given to the controller is only 40 rounds a minute. Okay? So the control gets bad data. That's one thing that can happen because of this compromise. Also, if this link is compromised, then the actuator gets bad data. So the actuator was supposed to be set on, but it is actually set off, or it is not set on. So these are some of the attacks, and then the network could be jammed, in which case the controller either does not get the data from the sensor, or is not able to send data to the actuator. So these are some very serious attacks that, in fact, if they happen, if the attacker is successful, it is very difficult to then find out what should be done with the system that is continuously operating and on which the lives of huge number of people in a country or in a city depend. And of course, one of the worst cases that can happen, which happened with the Stuxnet, is that the control system itself is compromised. So Stuxnet actually compromised the entire system, and therefore nobody was able to detect it for a long time. Okay. And of course, then there could be physical attack on the system also, which is possible through internal means or through natural causes. So let me now, with that background, let me now go into what we mean by security and safety levels. So we consider a cyber-physical system to be completely secure if all possible single and coupled attacks are detected by the defense mechanism. It is important to note that the single attacks are sometimes easier to detect than coupled attacks. If I have time, I'll point that out a little later. By coupled attacks, I mean attacks that are made in that part of the system and in that part of the system. Only when you make those 2 attacks or 3 attacks, only then the system will really function poorly. Otherwise, it will continue to function or detect the attack and recover. A CPS is considered completely safe if it never moves into an unsafe state after an attack is detected. So I'm assuming that the attack has happened and the attacker is successful, and now we want to make sure the system never enters the unsafe state. Okay, so what are our goals in the design and testing of such cyber-physical systems? A designer's goal is to design a completely secure and completely safe CPS. Obviously, easier said than done. And a tester's goal is to estimate how secure and safe a cyber-physical system is. Okay? So both are extremely important goals. So past work, by the way, a lot of work has already been done in this area. I think the pioneers are from Berkeley, Shankar Shastri's group, and then his students, Saurabh Amin, who is at MIT. And they have done a lot of work in this area, but a lot more needs to be done. And I'll point to some of the work that they have done and some of the how we can move forward. So this, I'll just describe briefly an experiment that was done by a team of researchers at Berkeley. And this paper appeared in 2011. Cardenas was one of the PhD students, and so was Saurabh Amin and two others. Their goal was to assess the effectiveness of statistical methods for attack detection by using knowledge of the system's physical behavior. What I mean by physical behavior is, let's say if there's a tank, if there's a pump which is sending water into the tank, the outlet of the tank is closed. If the pump is on, then the tank water level must go up, unless of course there's a leakage in the pump. If the water level is not going up and the pump is on, outlet is closed, then there's a problem if the water level is not going up. So that's an example of physical behavior. There are many such examples of physical behavior in our system. So the question is, can we detect the attacks with the help of the physical behavior of the system? And I think that they were probably some of the first researchers to do that. So they looked at 3 different types of attacks. They called something called surge attack, bias attack, and geometric attack. I won't go into the details of these attacks. Those of you who really want, you can look at the paper. These are the 3 different types of attacks they looked at. And what they did was, they did the experiment on a simulator. not on any real system or not any test bed for a real system. So they did it on a simulator. So the simulator is, the overall structure of the simulator is shown here. There is a reactor in which 3 reactants come in through different valves, and they react inside this reactor. The goal, of course, is to make sure that the safety goal is to make sure that the pressure inside the reactor never goes beyond a certain maximum limit. And then, of course, there are several sensors here that are monitoring various parameters or various state variables of the system to make sure that the system is working properly, and also making sure that the output, the product that is created, is the right product. So they did their experiment on this system, which is a simulation system, and there are 3 sensors that are used here. So they actually tried to attack these sensors again in simulation, and then they used a method for detecting these attacks. And when the attack was detected, then they used another method to find out whether they can make sure that the system remains safe. So that's in brief for the experiment. Of course, these 3 are the sensors which are the key attack points in the system. The detection technique they used was something called change detection, which is detect possible change at an unknown point during the trajectory of the system. And they used something called QSUM method, cumulative sum, which is a non-parametric statistical method for detecting changes in the data that is coming in from some source, in this case from the sensors. The conclusions were that the anomaly detection method that they used, module that they used, was able to detect and respond to all attacks. It was a very interesting observation, and of course they made a claim that because they were using the physical properties of the system and the physical model, linear model of the system, and the statistical method, therefore they were able to detect all the attacks. So it was quite good actually. And they also said ADM is fast enough so that attacks do not cause any damage to the process, that the tank pressure never exceeds its maximum limit. So remember that the results of this experiment are on this simulated experiment. So we at SVTD wanted to know, okay, suppose we conduct a similar experiment on a real cyber-physical system and apply the same techniques, what will be the outcome, whether the outcome is the same as that of the Berkeley experiment. So we are still in the process of doing that experiment. I'll just show you some initial results. The final results will be known probably in a few months. So what we did was to take this robot. It's a nice $4,000 robot called the Amigo bot, and the Amigo bot has 8 sonar sensors, 4 in the front, 2 on the side, and 2 in the back. And we actually created a simple experiment that this robot has to deliver, let's say, milk to near this wall, and there's a controller that is controlling this robot. The milk has to be delivered somewhere here, and there's an attacker that is sitting here. We are controlling the robot through wireless network. So the controller and the robot are connected through wireless network, and the controller essentially sends a control command to move the robot forward or to stop. And of course, the controller is also getting data back from the sensors to indicate what is the distance of the robot to the wall, and the robot comes to this point, it should stop. So this is the no entry zone. But the attacker, we had a student from France, and one of our students, they actually spent about a month to find out how to attack this robot, and that's how this experiment was set up. So these are the link in the attack point. Now, we wanted to investigate the effectiveness of the QSUM method. So what we did was, the attacker's goals are to create, to crash the robot to the wall, or to overrun the destination, or it does not reach the destination. If any one of these things happens, then the attacker is happy, and the Amigo bot fails in completing its task. Okay? So this was our experiment. Of course, our focus was primarily on crashing the wall, but even these 2 objectives, if they are met, then the attacker's goals are met. So the initial results are somewhere, I won't go into the details, but I'll just give you an idea. So we used about 6 different attack detection methods. Some of them are the same as the ones used by the Berkeley experiment. So we have simulation results as well as the robot. As you can notice here, in the simulation, all the detection methods were able to detect the attack, whereas in the actual robot, only in this experiment, only 2 are able to detect the attack. Now, the experiments are different in the sense that we have different goals, and the results and the setup is slightly different, and therefore you see the different graphs. So in almost all cases, we found that there is a significant difference in the simulation outcomes and the actual robot outcomes. And this happens almost every time. So our initial observations are the results obtained from simulation differ from those obtained in the experiment with the real robot. Maybe you might say, so what's the big deal? We would have guessed it even otherwise, that the simulation result will be different from results from the real robot. Well, but of course we have first thing is that we have shown it, and then we also want to find out why is that the case? Why is it that the simulation results are different from real robot results? And the main reason, of course, is that the main reason is that the robot sensors are not always perfect, whereas the simulator the sensors are perfect. Now, imperfect sensors are also modeled, but imperfect sensors are modeled using some kind of a Gaussian or some kind of a statistical distribution, and the attackers are not following the statistical distribution. The attackers are following some strategy which is almost impossible to model using traditional statistical distributions. So QSUM, which is a method that Berkeley used, is effective in detecting attacks in a simulated environment, but not in real environment. And the robot crashes or fails to meet its requirements when QSUM fails to detect the attacks, which means the system is not secure and the system is not safe, both. Okay, some attacks, even when detected, will fail to stop the robot from crashing. Even when you detect the attack, it takes time for the system to respond to the attack, and by the time the response is set, that is, the robot should stop, the robot has actually already crashed into the wall. Now, this is a very, very simple example. We are looking at large, very large systems that are thousands of times more complex than the robot. But we wanted to start small and see how these things work in a simple system, and then apply them to a much larger system that I'll show you later. So, of course, how to ensure that the robot never crashes. And of course, this question is extremely important, but you can reframe this question for a water power plant or water treatment plant or for a power generation plant. So what we are now thinking of is to create some kind of a defense mechanism so that even after the attacker is able to get into the system is able to detect that, well, there is something wrong going on in the system, and it never moves the system, it never lets the system move into an unsafe state. So what I'm showing you here is what I call orthogonal defense architecture. The diagram does not show everything, that's why I'm calling it partial. So assume that there are n components in your system. So these could be generators, boilers, furnaces, or water tanks, etc. And then you have these PLCs, programmable logic controllers, that are controlling these components. What we do is we attach to each component, or each, let's say, critical component, what we call as local intelligent checkers. These are we call them LIC, local intelligent checkers. These intelligent checkers communicate to the PLCs via a reconfigurable intelligent checkers network. The important point to note here is that the checkers are only sending data, they are not receiving anything. So an attacker cannot go into the checker. The attacker can only read the data that is coming from the checker, but not go into the checker. But then there could be situations where the attacker is manipulating the system in such a way that you need to get the state of multiple components to find out whether the attack is going on or not, and for safety. And so we also have global intelligent checkers, which of course are communicating both ways through this reconfigurable network. Of course, we are assuming that this is an independent network. It is not the network that is being used in the existing system. It is a separate network and hopefully designed so that it is much more secure than an existing network. And when you do that, first of all, you are raising the bar on the difficulty of attack, and also you are at least making sure that the local intelligent checkers cannot be attacked through the network. Of course, they can be attacked physically. If somebody gets into the system, physically they can attack. So that's our orthogonal defense architecture. And then, of course, this is also going to a SCADA system for more monitoring and control. Now, so the problem now we have, which we have not yet solved, is how to find out how secure is my cyber-physical system and how safe is my cyber-physical system. So when I ask my friend in the water plant these two questions, they have no idea. Of course, some of the youngsters say, oh, it's perfectly secure. But the more mature people say, well, we don't know, because we have never done a quantitative assessment of the security and safety of these systems. Of course, assessment is always done, but those are more management-oriented assessments where there are check boxes. Okay, have you done this? Have you done this? Have you done this? And so on, rather than more engineering and technically grounded assessments. Okay, so now I'll quickly define level of security as the effectiveness of the detection mechanism, and level of safety is the effectiveness of the response mechanism. So I will say that I can define a metric. Let's say I can define it between 0 and 1 or 0 to 10. 10 means it is completely secure, 0 means it is completely insecure. In a realistic system, it will be somewhere in between. Okay, so now, before I give you the procedure, let me give you a hypothesis. This is a hypothesis, and the hypothesis is created based on our experience and observation of real life systems. So let's say you have a cyber physical system, which is 100% secure and 100% safe. Okay, let's say we have a system like that. Now, there are an infinite number of other cyber physical systems, which don't exist of course, but which are not 100% safe and 100% secure, but are pretty safe and pretty secure. In fact, all the systems that exist today in the world, almost all of them, are quite safe and secure. After all, we are getting our water, we are getting our power, and not many people are able to attack them to cause major disturbance. So most of these cyber physical systems that exist today are quite safe and secure. But they are not here. And we of course don't know how far they are. So the hypothesis is that a designer of these systems, or a team that designs these systems, is a competent person. And what that means is that the system that is designed is not far from a highly safe and secure cyber physical system. Okay? So that is the important hypothesis on which the procedure that I'm going to describe is going to be used. Do you have still have time? Okay. I don't want to take your time, too much time on this. Okay, so what I'm going to define is something called an attacklet. An attacklet is a simple method for changing something in the system. For those of you who are into software testing and who know about mutation testing, they will find quite a close relationship between attacklets and mutation operators. So here's what we do. Assume that there is an attacker wanting to attack a cyber physical system. The attacker generates an attacklet, and the attacklet is applied to the cyber physical system. So for example, there's a sensor in the system that is sensing whether the generator is on or whether what is the temperature of the boiler, and that sensor is sending the temperature to the controller, the PLC, and let's say we remove that wire. Okay? We just remove that wire. So that's an application of an attack. Now, when you do that, you modify this CPS to another attacked CPS, and this is the original one, this is the infected CPS. So for example, this attacklet is simulating malware or wireless link takeover or destruction of a physical component. So the attacklet is a very generic concept. Now what we do is, let me now define what do I mean by coupled attacks. So two or more attacks are considered coupled when none of them can individually evade the defense mechanism, but one application of an attacklet generates first order CPS and multiple generate higher order CPS. So if I want to generate a coupled attack, then I have to apply at least two attacklets. And a attacklet domain, of course, is physical components, logical components. So for example, you can apply the attacklet on a pump, on a tank, or on any of these physical components. So let me not go into details. So the question is, are there some useful attacklets? Not useless, useful attacklets. And that's an experiment that we are going to perform to find out what are useful attacklets. In software testing, this experiment has been done more than 30 years ago, and we have very good answers. But for cyber physical systems, we don't have an answer. We have some answer, but not statistically validated answer. So we do not know what are all possible attacklets. Can we construct a procedure with useful attacklets given the design of a cyber physical system? So attacklets, as I said, model known and unknown attacks. That's the important point. Most of the security work today is based on known attacks. So all the McAfee and all these security software that you get on your PC, that assumes that has knowledge of known attacks. It has the profile of known attacks and it is able to detect them when they happen. But when a new attack comes, only after they know about the new attack, then they are able to create software to detect those attacks. We want to create a procedure so that even unknown attacks can be checked for before the actual attack happens. So what we are doing at SCTD is to create two test beds. One is water and the other is for power. This is the design of a water test bed, the physical part of the water test bed. I won't go into the details, but as you can see there are 6 boxes like this. So the water is coming from the raw water source through a pump, it is mixed, and it goes through the raw water tank, through an ultrafiltration system, and so on. So this is our system that will be available sometime in February next year for experimentation. And people here in Colombo can come and actually do the experiments on this. We have designed it, and it will be working at SCTD in February. This is the communication and the control structure of this one. So we'll have both these systems together in a large room for conducting experiments. Now, let me give you an example of a single and coupled attack. So we have in this system, we have an ultrafiltration system. Your feed pump is sending water here, and there's something called a backwash process that is actually used to wash the membranes inside the ultrafiltration system. There are 2 sensors, one on this side, one on the other side. This sensor is sensing what is the pressure of the ingoing water, and this is sensing the pressure of the outgoing water. If the pressure drop is too much, then the membranes are actually stuck, and membranes need to be cleaned, and then the backwash kicks in. This is an automated process. But what can an attacker do to destroy the membranes? So, if P1 is greater than P2, P1 minus P2 is greater than tolerance, then an alert is automatically sent. But now, let's say an attacker wishes to damage the filtration system. They install a malware in the PLC for controlling the backwash, and the malware changes the backwash cycle. Okay? The pressure drop gradually increases across the UF system. It is detected by the PLC using pressure sensor measurements, so the operation manager is alerted. So an attacker fails in this case. Okay? Just simply putting a malware to change the cycle will not work because the pressure sensor will detect there is a problem and the operator will be alerted. So this attack fails. That was the first order attack. Okay? Now let's say the third order attack. What happens here is that the malware is of course intended to disturb the backwash cycle. It changes 2 pressure sensor readings used to detect the drop. Both the pressure readings it changes, not just one. And pressure drop gradually increases but remains undetected. Okay? So eventually the filtration system is damaged and our output water quality is unacceptable. So by actually attacking, installing the malware and attacking 2 pressure sensors simultaneously in a way that the control system is never able to detect the difference in the pressure, which is too large actually. It still thinks that the pressure difference is within the tolerance. So the attacker is able to get into the system and destroy the filter, the membrane. So that's the example of a coupled attack. Now very quickly I will tell you how we are working on a procedure for known and unknown attacks and finding out how good our CPS safety and security is. So we have a CPS, we have an attacklet applicator which will actually apply an attacklet on the CPS. We get a new CPS. Notice that this is slightly different from this. Remember the competent designer hypothesis. This is slightly different from this. And so now we either initiate the operation, we either apply the attacklet before we start the cyber system or while the cyber system is working. Okay? Now we find out whether this attack is detected or not. Remember, we are finding out how good is our defense mechanism, the orthogonal defense mechanism that I mentioned. We are trying to find it out. If the attack is detected, then of course, if the attack is not detected, then our CPS system defense mechanism will be, we need to update that. If the attack is detected, then we want to check whether the response mechanism is adequate or not. And if it is not adequate, then again we need to update the response mechanism. If it is adequate, then we apply another attacklet. So we keep on doing this procedure until all the desired attacklets have been applied and we have been able to update the system whenever we found a weakness in that system. So this is a procedure that we have come up with for quantitatively assessing the security and safety level of the system, which is based on the notion of orthogonal defense. So of course there is something called mutation analysis, which says that the attacked CPS behaves exactly the same as the CPS. If that happens, then the defense or response mechanism is weak. or CPS and CPS-A are equivalent, which means the attack rate did not make any difference. In case of this, we improve the defense mechanism or the response mechanism. In case of this, we need to show mathematically or through some arguments that the two systems are the same, which is a very difficult problem. So what do we get finally? We get a practical automated procedure for the generation of strong attacker models, a confidence metric for CPS security and safety, and a procedure to identify weaknesses in the defense and response mechanisms of a cyber-physical system. Challenges for this procedure: when do we apply the attack rate? Before the system starts or during the application? What are the appropriate attack rates for a given cyber-physical system design and domain? So we are working with Singapore's PUB and SingPower closely to determine what are the good attack rates that we should experiment with on a test bed. We will not do the experiment on the real system, we do the experiment on a test bed which is realistic, which is similar to the real system. And then how long should one wait to decide on the outcome of the experiment? Many attackers just sit there for quite some time, and it's a long time after the attack is successful, the attack will actually take place, even though the attacker has installed the malware in the system. So where do we go from here? We want to create realistic attack rates, we want to experimentally assess the attack rate procedure, and we want to develop an experiment with response mechanisms. Thank you. Any questions? Yes.
Thanks for sharing your experience. I'm Tony from Queensland University of Technology, Brisbane. I have one observation with one of your incidents of the SCADA Queensland. Second one is my question. The SCADA incidents in Queensland about the sewerage is not necessarily a cyber attack. It is a man-made, some kind of blunder rather than cyber attack. I'm not sure you will agree with that. Second question is, we spend a lot of time and money and resources trying to protect our system. Still our systems are not protected. There's a saying to say, unless all safe, no one is safe. So our system is not safe. Have you spent time or money or resources to understand what is the human factor behind attackers, in particular, why people are attacking the system? What is the motivation behind it? Is it psychology or craziness or economic motivation?
A very good question. Thank you. So the answer to your second question is no. I have not spent time in that psychological analysis, but I know there are a lot of people out there who are doing this. They are psychologists and social scientists who try to work on exactly these kind of problems. From what I have heard and I have read is that the motivations vary a lot. The motivation could be simply to say, hey, I got this, I got these guys, and that's it. They just become one level higher in their friend circle. The other more sort of dangerous motivation is that of states, rogue states or states that don't like another country and they have infinite resources to attack the system. And so that's another psychology. That's not psychology of an individual, that's a psychology of a state, of a government and so on. So there are many other such reasons why, motivations why people do that. And we are not really focusing on that aspect. We are focusing on the economic aspect. That is, when you actually implement security solutions on a system, you can spend several $1 million or only several $100,000. And the question is, what do you gain or what do you lose when you do that? So that kind of those economic models we are working on. But the psychology, in our team there's no one who's a psychologist who's doing this, but many other people are. The first question you mentioned, so from the, of course, I was not there at the Queensland attack when it took place. The only thing that the analysis says that there was an individual who was fired, but his account was not removed, and so this person went out and actually logged into his account and then did things so that the water system, the sewage was spilled. I would not disagree with you when you say that it was not a cyber attack, but it was. I would partially disagree with you, partially agree with you that it was a part of cyber attack. But of course, if there was a defense mechanism against that cyber attack, then this probably would not have happened. So yes, it was a physical flaw as well as a cyber flaw. It was both.
have caused a nuclear explosion.
Sorry,
The Stuxnet attack in Iran.
yeah.
Do you think that it could have caused a nuclear explosion?
Okay, if you look at the Stuxnet attack carefully, finally what the worm was able to do was to take control of the controllers and the entire monitoring system, and the centrifuges were being, instead of rotating the centrifuge at about 120 rotations per minute, I think that was there was a maximum speed limit. It was rotating it at a higher than maximum allowed speed limit for a short amount of time, and then again coming back to very low speed limit, then again going to normal, and then again going to much higher than. So that was the approach that the Stuxnet worm used in order to destroy that centrifuge. But the centrifuge destruction does not mean that there will be a nuclear explosion, because all that the centrifuge was doing, there was uranium fluoride, and there's 2 or 3 different uranium isotopes that were going in there to produce uranium which is enriched uranium. So there was no chance, I don't think there was a chance of explosion there.
Professor Mathur, yeah. If you replicate the PLCs and take the majority decision of those which are currently working, wouldn't the system function?
Yes, so actually that is already being done. So the PUB at Singapore, for example, and most other cyber-physical systems, they use hot and cold PLCs. They always use hot and cold PLCs. The problem is the following, that, so one of the problems we are working on right now, Sunjin, one of our faculty members is working on this problem, is that suppose I am an attacker and I install, and I am successful in installing my malware in both the PLCs, in both hot and cold PLC. So in that case, one has to use some kind of an attestation procedure, online attestation procedure, which works sort of every few seconds or every few minutes to check if the code that was originally installed in the PLC is the code now. So this attack will not, having redundant PLCs will not take care of this attack. And there are many attacks where redundant PLCs will simply fail. That is not possible to detect just based on redundant PLC. Redundant PLCs are very good when the hot PLC, which is actually working, detects a problem, and then there's a hot connection between the 2 PLCs, the hot and cold, and as soon as the problem is detected, the cold takes over, and then the hot is removed and replaced. So that those failures, system failures, are generally detected by hot and cold. But strategic attacks like malware, etc., no, they will not be detected by redundant PLCs. Something else here? Okay, thank you very much.